Today we're going to talk about section 1.4 from your book, Extrema and Average Rates of Change. In the past we've talked about functions. You guys know about functions. We can do vertical line tests in order to decide whether or not we have a function. We can describe functions in other ways. So a function can be described over a given interval as increasing, decreasing, or constant. So here we're clearly talking about slope, right? An increasing function means that an increase in x results in an increase in y. So as we get bigger on our x, we get bigger on our y, results in this, right? Our lines look like this. So this gets bigger, this gets bigger. A decreasing function means that an increase in our x results in a decrease in our y. So as we increase x, x gets bigger, y gets smaller, right? This is the negative of y. So our function looks like this. This is a resultant function. We have functions that go this way. A constant function means that an increase in x results in no change in y. So for increasing functions, we have, this is a positive slope. For decreasing functions, we have negative slope. And for constant functions, we have zero slope. If you have something that looks like this is undefined. You ended up with 0 in the denominator. We have undefined slope. This is not a function. Zero slope, however, looks like this. So you have an increase in your x and no change in your y. So if we had this being your y-axis, this being your x-axis, this could be your function. Increase in x, get bigger and bigger, bigger on x. No change in y. So if we were to plot this, we could have functions that look like this. So on this interval right here, we went from here to here. We have an increasing function. From this point to this point, we have a constant function. And from this point to this point, we have a decreasing function, or negative slope. Let's look at an example. So it says, use the graph of the function to estimate the intervals over which the function is increasing, decreasing, or constant. Support numerically. So if we look at this function, we see we start really, really high, infinity, and then as we move to the right, which is what we're doing, right? We're moving in the positive x direction. Looks like we get smaller and smaller, continually decrease our values. So as x values increase, our y values appear to decrease, right? As we move farther and farther to the right, our function goes smaller and smaller. It goes lower and lower, more and more towards the negative infinity on the y-axis. So our y values appear to decrease. Therefore, f of x, we assume, is decreasing. And where is it decreasing? Is there any point where it's not decreasing? It looks like it's decreasing everywhere. So we would say that this is decreasing from negative infinity to positive infinity. So in order to check this numerically, we can construct a table of values and plug them into our f of x. So I have negative 100, negative 10, negative 1, 0, 1, 10, 100. Our f of x is equal to negative 2x cubed. So we plug these values in. We get positive 2 million. Then we get positive 2,000. Then we get 2. We get 0, we get negative 2, negative 2,000, negative 2 million. So we can see it looks like the entire time we're following this pattern, we start out really, really big and we get really, really small. So we'll agree, yes, check. We are decreasing. We checked it numerically. Okay, example 2, use the graph of the function to estimate the intervals over which the function is increasing, decreasing, or constant. Support numerically. Okay, so if we look at this, we have g of x equals x cubed minus 3x. It looks like we have a curve up, and then we get to some point, we have a curve down. We get to some other point, we curve back up. So the point that it looks like we switch at is negative 1. Then it looks like we switch back at positive 1. So from negative infinity, because it looks like forever if we went really, really far down here, we're going negative infinity, we get to 1, we're increasing, then from negative 1. So from negative infinity to negative 1, we're increasing. We get from negative 1 to positive 1, we are decreasing as we move to the right along our x, which means positive x. We are decreasing our y, so that's a decreasing function. Then when we move from 1 to positive infinity, to the right on our x, we go to positive infinity on our y. So that means we have an increasing function again. So viewing the graph from left to right, y values appear to increase between negative infinity and negative 1, then decrease between negative 1 and positive 1, then they appear to increase again between 1 and infinity. You'll notice I didn't use brackets here. We're not exactly sure what's happening at these points. We're not sure if that is an increase or a decrease, so we leave these as parentheses. Therefore, we can't say anything about g of x increasing or decreasing the entire time because we're looking at each interval. So during the interval of negative infinity to negative 1, we increase. During the interval of negative 1 to 1, we decrease. During the interval of 1 to infinity, we increase. In order to verify that we're not crazy, we construct a table of values and check. We set this table of values to the same intervals. Shocker. So we'll look at, I already plugged in some values for these. We have x is equal to negative 13, then you do your f of x. So you plug that x into x cubed minus 3x. Came up with negative 2158. For x is equal to negative 11, you come up with negative 1298. For x is equal to negative 9, you come up with 702, excuse me. So you'll notice as you're increasing your x, this is getting bigger, bigger, bigger. You are decreasing your f of x. Does that match what we said? I'm sorry, you're also increasing your f of x. Welcome to my brain, it's early. Okay, so let's plug in negative 7, and you get negative 322. This is also a bigger value, more positive value, less negative value. For negative 5, you get negative 110. For negative 3, you get negative 18, more positive. So we're increasing. We're getting bigger and bigger. This does match what we thought. Okay, so we expect to be decreasing from negative 1 to 1. So as we move bigger on our x, more positive, more positive, more positive, what is our f of x doing? It appears to be moving more negative. So we go from 1828 to 1375 when our x goes from negative 0.75 to negative 0.5. We plug in value 0, we get 0, negative 1.375. You guys can fill in the rest of this table if you want. So on our last interval, we move from 1 to infinity, and as we see, our x gets bigger, 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 bigger. Our f of x also gets bigger, 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 bigger. So we are following everything we assumed. We looked at the graph, we analyzed graphically, we checked. It's important to know that we don't describe functions as increasing, decreasing, or constant at a point. So at a point on a graph, if you have this point right here, we don't call this point increasing or decreasing. We might have some maximum or minimum, but you only call it increasing or decreasing over an interval. So if I'm asking you where it's increasing or decreasing, I want to know from where to where. Okay, let's talk about Extrema. So you know Extrema, extreme sports, it's like the most something, right? So Extrema, when we talk about Extrema, we're talking about critical points where a function changes its increasing or decreasing behavior. This is a really unfun way to know about this, but it's true. A more obvious way to know about it is it's the most, right? You guys are familiar with Extrema already in the terms of maximum and minimum. And you know that it's changing direction. We just talked about increasing. We can tell that this is a maximum up here. And if you know that this is an increase and this is a decrease, it seems obvious that you have an extrema right here at the point where you change. Similarly, this is a minimum. You went from decreasing to increasing. You have an extrema at a point where you change direction. So a maximum, the function changes from increase to decrease. Minimum, the function changes from decrease to increase. If you're not sure, draw a picture. We have different kinds of maximums and minimums. We can have a relative maximum, which is just a maximum on some interval of the domain, or you can have an absolute maximum. Which it means the maximum for all of the x. It's the most maximum for the whole domain, for everywhere, the biggest, the most. Okay. Similarly, you can have a relative minimum, pretty sure there's way too many letters in that, and an absolute minimum. Okay. I don't know how to spell the word minimum. The last thing we need to know is you can have a point of inflection. The point of inflection is where the curve of your graph changes from open up to open down or vice versa. So let's talk about relative maximums and minimums and absolute maximums and minimums by looking at this graph. So we have some open ups, some open downs, we have some A's and some B's. We have some maximums that are higher than some other maximums and some minimums that are lower than some other minimums. So the minimums that are the very, very, very lowest are going to be the absolute minimums. The maximums that are the absolute, absolute, absolute highest are going to be the absolute maximums. So for example, B is an absolute maximum. C and A are relative maximums. They occur when we go from an increase to a decrease, but they are not greater than B. Similarly, F is an absolute minimum because it's the greatest, most absolute minimum. G and E are relative. They occur when we go from a decrease to an increase, but they are not greater than F. It is also a relative maximum. A point of inflection, if you look, we have this open up, then we have some open down, right? This point right here in between we have some point where we're changing. If we change our curve, all these curves, all of these points where we change what that shape looks like, those are points of inflection. Any of these, I'll make those a different color. These are points of inflection. Any point where we change the shape of the curve. Average rate of change, we'll talk about this quickly. It's pretty simple. It's just the slope of the line. You guys know slope. Slope is just rise over run, delta y over delta x, change in y over change in x. So if you have this line right here, you guys know how to find slope. You just take this point, we'll call that 4, 3, and this point, 1, 2. Take the 3 minus the 2 divided by the 4 minus the 1. It's really simple. So if you were given this graph over here, this f of x, and you wanted to know about the average of the rates of change of here, if you wanted to know about all the averages of all the slopes from this point to this point, from x1 to x2, the only thing you need to do is take those 2 points, x1 and x2, and you need to find the slope of those points. The way that you do that is you take f of x2 as your y minus f of x1. So that's our x. When we talk about slope, we also say y2 minus y1 over x2 minus x1. So this f of x2 becomes your y2. F of x1 becomes your y1. And then you divide that by x2 minus x1. That's just x2 minus x1. It's the exact same thing. It's going to give you your average rate of change. So in an example, if we were given f of x is equal to negative x cubed plus 3x over the interval -2 to -1. So our x2 and our x1, this is this right here. So x1 is -2, x1 is -2, x2 is -1. It's not confusing at all, I'm sure. We plug those in. So what do we plug those into? F of x. So we have f of x2, that's our y2, right? y2 minus y1 over x2 minus x1, delta y over delta x. We're trying to find slope. We're trying to find rate of change. So we plug that in. We get f of -1 minus f of -2 over -1 minus -2. We come up with this really long equation, but all we're doing is we're substituting these values into this one at a time. Do it once here, then you're going to subtract it, and then you're going to divide it and subtract your x values here. Come up with -4. That's your answer. You can do it again with 0 and 1. Again, you're just going to substitute those values into this equation.